Good morning, everyone. Today, my name is Ryan. Welcome to my YouTube channel live stream. Today, I will be talking about optimizing Node.js performance, V8 memory management, and GC tuning. Prevent crash and improve latency by understanding and tuning V8 garbage collection for your Node.js application. A common observation for Node.js developers is the seemingly continuous growth of their application's memory footprint, often measured by RSS, also called as resident set size, reported by the operating system. This increasing RSS frequently leads to concerns about memory leaks. As a result, many production environment config monitoring or orchestrating tool like Kubernetes or Docker so on to automatically restart or terminate Node.js process with their RSS surpass a certain percentage of the allocated memory. Often around 80% this is done using RSS equates to a critical memory problem requiring intervention. However, it's crucial to understand that high RSS in a Node.js application does not automatically signify a memory leak in conventional sense. V8, the underlying JavaScript engine, employs sophisticated memory management strategies focusing on performing optimization on key aspect. It is tendency to retain memory segments acquired from operating system even after JavaScript objects with those segments have become garbage. V8 holds onto the memory proactively anticipating future allocation needs, thereby minimizing performance, cost of frequent memory requests, and reach to OS. This reserves not but not actively used memory. A real memory leak involves unreachable JavaScript objects that the garbage collector consistently fails to reclaim, leading to an unbounded increase in memory actively used by applications heap over time. A high but stable RSS or an RSS that grows but periodically decreases after a major garbage collection cycle indicates that V8 is managing its memory pool effectively for the given workload. Relying solely on RSS as an indicator for process termination can be misleading and may result in killing healthy applications. Accurate diagnostic requires inspecting V8 internal heap statistics to differentiate between V8 memory management and actual leak which the usage identifies. Understanding V8 generation garbage collectors. The V8 engine's garbage collector is built upon the general generational hypothesis, a widely acceptable principle in garbage collection theory. This hypothesis posits that most objects a program allocates become garbage shortly after creation, die young. In contrast, objects that persist beyond an initial period tend to remain alive for much longer. V8 organizes its heap memory into distinct generations to capitalize on this behavior, primarily the new space, young generation, and the old space. All new JavaScript objects are initially allocated within the new space. This area is kept relatively small and is optimized for frequent high-speed garbage collection using an algorithm called savage scavenge divides the new space into equal semi-space objects. Objects are allocated into one semi-space until it fills. At that point, a scavenge cycle begins. V8 rapidly identifies live objects in filled semi-space by traversing reachable objects into second current empty semi-space. After they copy the first semi-space containing only garbage is collected clearly. The role of semi-space and swaps this. This is the diagram where the GC runs. So surviving objects are copied to a from space to space from space to space table. Objects that survive the two GC runs are moved to an old space. Objects that endure through a couple of these swap scavenge cycles, typically two, are deemed likely to be long-lived. These surviving objects are then moved from the new space into significantly larger old space. The old space is intended for objects that long life cycles. Garbage collection in old spaces performed less frequently because it is more time consuming. Its primary use is mark and sweep. algorithm. V8 traverses this entire object graph to mark all objects still reachable from the application's root. Optionally, V8 may perform a compact phase, rearranging the remaining live objects to reduce memory. V8 often retains this compact space and optimizes future old space. The performance pitfall: premature promotion. Despite its efficiency, generational gap collection garbage can sometimes lead to performance degradation, also known as tuning V8 configuration. To address performance challenges caused by premature promotion, particularly in applications that high allocate churn, Node.js developers can directly influence V8 garbage collectors' behavior by tuning the size of young generation new space. This flag allows us to specifically maximize size in megabytes for each two semi-spaces and increases. Strategic trade-off: memory for compute performance. Modify the max semi-space sizing settings represents a conscious and often beneficial performance tuning decision that involves trading memory resources for computational efficiency. Max semi-space sizing. In many product environments, especially within cloud infrastructure or containerized departments, RAM is often considered more abundantly and less expensive resources compared to CPU cycles, as the business impact of poor application responsive. Therefore, deliberately allocating memory behavior infrastructure but can yield significant performance. Node v22 default and low memory consideration. The essential nuisance in V8 memory management and embraced around Node.js v22 release cycle concerns how the default size for new space semi is determined. Then there is memory tuning in practice. You have a diagram where database querying, synchronized processing, also the ideal way HTTP request comes in and goes out. In a Node.js application, then you have let's run benchmark on standard configuration. If you have on your AutoCAN, it gives you 30k request in 30 seconds. Similarly, next steps. Yep, there's a talk by this guy at .js 2025 for working. Thank you for tuning in. Bye.